So hello everybody, welcome to this week's Science UIL. Osmond's not here today because he's sick, but that is actually a good thing because I'm going to be talking the whole time about the Standard Model with quantum mechanics, quarks, hadrons, bosons, leptons, neutrinos, neutrons, protons, all that fun stuff. Yay! So can anyone raise their hand and tell me what a quark is? Does anyone have any idea what a quark is? Nathan, Shazib. I want Shazib to say.
It's what makes up a proton.
It's what makes up a proton, right. And to start off today's meeting, we're going to watch a video by Hank Green called Strange Charm, a song about quarks, link in the doobly doo.
Good morning, John. I can already hear the music building up beneath me, so I should probably just stop talking. This song is about quarks. I wrote it. It's called Strange Charm.
A quark is a fundamental constituent of matter, observed in 1968 through deep elastic scattering. We found that protons aren't as simple as we thought. We thought they were solid particles, but they are not. Protons, in fact, are made up of 3 separate pieces. It just gets more confusing as our knowledge increases, but that is what a quark is. It's a piece of a proton, and they also make up other things, including a neutron. Oh, up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with leptons and bosons, and the something that missed, they make up everything that we can see and that we know exists. Things made up of quarks, including protons and neutrons, are composite particles that physicists call hadrons. Many types of hadrons are theoretically described, but most exist for only very brief amounts of time. Quarks have electric charge, color charge, mass, and spin, and having color charge exists solely inside of other kinds of particles and cannot exist alone, which is why quarks have never been studied on their own. Up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with leptons and bosons and the something that missed, they make up everything that we can see and that we know exists. Quarks can join together in 2 different ways, baryons and mesons, but most instantly decay. If a particle has 3 quarks, then it's a baryon. If there's 1 quark and an anti-quark, then it is a meson. These tiny bits of matter are part of almost everything, and there is no unified theory to make it less confusing. But the fact that we've identified that they exist at all is so goddamn remarkable that I just sit in awe. Oh, up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with leptons and bosons and the something that missed, they make up everything that we can see and that we know exists.
I like that song. That's a good song. I hope that you all enjoy it too, and you can listen to it anytime by going to dft.ba/quarks. And that's possible because my friend Sam and my friend Alan worked their butts off to create dft.va, a URL shortening service that reminds you and all the people that you tweet to not forget to be awesome. So yes, you can have your own.
Cool. So that is a song by Hank Green called Strange Charm. It basically explains the idea of quarks. So could someone other than Shazib and Nathan raise their hand and tell me what quarks are and how they relate to protons and neutrons? Even if you think you might be wrong, raise your hand. Raise it high. Rishi.
Okay. Well, they
Mysterious cameraman.
they make up protons and neutrons.
Right. They make up protons and neutrons. In a proton and neutron, how many quarks are there?
6.
3.
3.
3.
Okay, yeah.
Can anyone tell me if... Let's see. Can anyone tell me what kind of charge quarks have that make them special? It was touched on briefly in the video. I heard it? Color charge, right. So, from the video, I'm going to explain all of the stuff he just went over. And I'll be going through the Standard Model after I explain the basic idea of what anything is happening in this. So, a long time ago, early 1900s, late 1800s, there were people who were looking at the stuff that makes up matter and realized that there's a positive and negative charge pertaining to that. And everyone know who Ben Franklin is? He was actually the person who decided that electrons should be called negative and protons should be called positive. He figured there was some positive charge when you take, I think it was a glass rod, and you rub it with a silk cloth. There's a charge that is carried. And he actually got it backwards. The positive charge doesn't move, the negative charge moves, the electron. And by not calling the electron positive, he pretty much made everyone's lives more difficult for anything related to charge for the next 150 years and on. But the idea is that eventually, with Rutherford's gold foil experiment, they figured out, I want to use blue for this, they figured out that an atom has a nucleus with a bunch of positive charges clustered together, and then there are electrons dotted around at seemingly random positions. And Bohr said they orbit like in a circle, and as time went on, scientists figured out that wasn't true. And at some point, scientists figured out there are also neutrons, which have what kind of charge? Electric charge. Like what kind of electric charge? Louder. Neutral charge, zero charge. They are neither positive nor negative, which makes them understandably hard to detect. Because if you have a charged plate, like a positive or negative plate, or you have a magnetic field, then electrons and protons will move in weird directions, but neutrons will just keep going straight. Now, over time, when people started accepting that this existed, that there was a cluster of positive charges and there were dotted negative charges around it, people began to ask why. So specifically, why does the electron have no volume? Why is it just a dot? But the protons and neutrons seem to be big spheres, like measurable spheres. You can detect the size of a proton. And they figured electrons must be a fundamental particle. You can't break it down. It's basically a point charge. But they wanted to figure out why protons and neutrons had size. So they did what anyone would do if you have two things, they want to figure out what they're made of, and they started hitting them against each other. So you take one egg, and you take another egg, and you smash them together. Oh, they're made of yolk. So that's basically what they were doing. So you get these particle accelerators, and you have protons here, you have protons here, and you start spinning them around and around and around and around and around and around, and you accelerate them really fast using magnets. That's what happens at CERN and Atlas and all that stuff in Europe. And they go flying together, and they go flying together, and boom, something happens. What scientists noticed was that you get these weird spirals of stuff, and they always seem to have particles that come back together. And they noticed that when you smash protons together, there are two positive spirals that would go one way in a magnetic field, and one seemingly negative one that would go the other way. And they worked out.
Please pardon the interruption, but will Richard Burgess...
I'm just going to talk over this. Can everyone hear me?
Richard
Okay.
Burgess.
So they figured that in a proton, there are three particles that makes it up. They had no clue why. This is just what they saw. They saw one tiny positive charge, another tiny positive charge, and one negative charge. And they saw that all of this made up a proton. And they figured that if these two were identical, they found that since the curves looked similarly, they had to be the same mass. And one was negative, apparently with the same mass, just the opposite charge. Then you have to have two positive identical charges, one negative charge. And mathematically they worked out that that positive charge has to have a charge of 2/3. And the negative one has to have an electric charge of negative 1/3. So 2/3 plus 2/3 plus negative 1/3 equals 1. And then they're like, okay, that's cool. Let's smash other things together. So they took neutrons and smashed them together, and they interacted. And things seem to interact the same way, only you got two negative charges interacting. So inside a neutron, you have one positive charge and two negative charges. So you get positive 2/3, negative 1/3, and negative 1/3. That adds to 0. And so they figured their math works. And they're like, that's cool. We have no idea what to call these things. They had no idea like what was happening, why it was happening, where it was happening, how it was happening. They just knew that it was happening because they had these cool pictures of it. They looked like spirals. If any of you saw the bright, obnoxiously neon shirts from physics last year, they have weird spirals on them. Ask any physics student, they'll probably be wearing one sometime in the next week. But those traces of spirals, Nathan, can you pull some up on this computer? Quark spirals, I guess. But those are the traces of that moving particles will leave through a charged field. And so they said, these things are behaving pretty quirky, let's just call them quarks, because they had no idea what to call them. Eventually they figured out that they have some other property that's always conserved. They're always kept in pairs, and there's some force binding them together. Since they figured that it was always in sets of 3, because they never found a single quark alone, they always found it in a trio, they called it color charge, because you think you have, in primary colors of light, you have red, green, and blue. So since that was the most convenient charge, or most convenient set of 3 that people can immediately recognize, that's what they call quarks. So up here, Nathan has brought up a picture of what spirals look like. If you have hydrogen gas and you put charged particles through it, you get these weird images appearing whenever a charged particle just travels. So these straight lines are things, I think probably neutral particles passing through. And then all of the spirals are the effect of a positive or negative particle going through a magnetic field. And you see some spiral in different directions, that means they have opposite charges. So moving back to quarks, they're like, this is awesome! We found these weird sets of stuff that seem to have no purpose in existing.
Please pardon the interruption, but
They
will
couldn't
Nash
figure out
Robertson
why
please report to
they would bind
142A?
together to make a
And
proton.
Simone
So
Savini,
they figured it was
please
really,
report
really,
to
really,
the
really,
main
really
office.
strong to
Thank
keep
you.
all of these sets together. So they called it the strong force. And actually they figured out that it's the same force that keeps protons within the nucleus bound together, even though electrically speaking, positive charge and positive charge close together should repel. So the idea is that with quarks, you always want to have red, green, and blue close together to cancel out. Like positive and negative charge with electric charges, you have them close together, and from the outside it looks like 0, it's neutral. Within a neutron, the net charge is added to 0, so there's no net effect. It's happy, it's in a bound state. So they just kind of randomly assigned red, green, and blue charges to the 3 different quarks within what they called a hadron, or just a combination of quarks. And so inside it you have a red one, and a green one, I can't write letters, and a green one, and a blue one. And when you're looking from way far away, you see red, green, and blue light, and it looks white. But if you step up real close, like to a projector screen, to the actual projector, you can see individual red, green, blue. And what happens is when you have another hadron right next to it, another collection of 3 quarks, then the difference between where they're located is actually noticeable. And so you have an incredibly strong force that's binding the quarks together within a proton, also binding different protons together. And they call it the strong force because it's orders of magnitude stronger than any other force we know. So from there, I'm going to step into a little bit of relativity. So anyone heard of some obscure German guy called Albert Einstein? Yeah, he made a pretty big hullabaloo in the early 1900s. He came up with 2 really famous equations. One everyone knows, 2 no one knows, but the people who do know freak out about it. Can anyone tell me what the popular one is? E equals